Hello and welcome to the video for section 3.1. Just want to remind you guys that probably the best way to utilize these videos is to take notes as you watch. Feel free to pause, rewind, watch multiple times any example that you see. The PowerPoints are in Blackboard, or hopefully you print those out and take notes on those as we go through these examples together. Okay, so overall the main idea in chapter 3 is we're going to talk about functions. In this textbook, we're going to assume that you've never seen the conversation of functions before, and we're going to introduce the concept and talk about pretty much all there is to know about the concept of functions in general. So the first thing that we'll want to do in 3.1, since this is an introduction section here to the whole chapter, we're just going to want to first of all determine whether a relation represents a function. All right, so in general, a relation is a correspondence between any two sets, and in an algebra course, we're going to typically use sets that are ordered pairs. So it's pretty classic in an algebra class that x and y are two elements in these sets, and we talk about plotting points x, y in a plane. So for example, on this line that we have plotted, x is 1, y is 2. Here x is 0, y is -1. And this equation, y equals 3x minus 1, describes the relation between all of the points on this line. So in general, a relation is any set of ordered pairs. And in just a moment, we're going to talk about when that relation actually can be described as a function. All right, now most of what we're going to do in this class is we're going to look at equations and their graphs, but there are some examples where we're going to look at what we call mappings, right, or ordered pairs. So here's a mapping from the set of states to the set of the number of representatives. So you'll notice that Alaska has 7 representatives. We'll notice that Arizona maps to 8 representatives, California maps to 53, so on and so forth. So this is an example of relation. In this case, a mapping from one set to another. This is sometimes called an arrow diagram. So we could think of ordered pairs, right? Here's Alaska and then its number of representatives. Here's Arizona and then its number of representatives. And then California and its number of representatives, and so on and so forth. So if we envision the relationship between two sets as a mapping, we could also envision them as ordered pairs in this fashion. Now again, the bulk of what we're going to do in this class is we're going to deal with numerical examples, right? But here's an example that doesn't necessarily have numbers, just to illustrate the concept. Now specifically speaking, right, if you were to take like an algebraic theory course, the domain and the range we call sets, and they can represent really any elements. And again, even though we're going to focus on numerical values in this course, these are concepts that really could represent any type of sets of elements, right? So a relation can map those elements in any way that it wants, but a function specifically requires that each element of x correspond to one and only one element in the range, right? So here's two examples, right? Here's a mapping, right? A relation that is not a function, and here's a relation that is a function. And let's look at why this first example is not a function. So if I look specifically at the element of Colleen, notice that this element in the domain maps to two different elements in the range. So we would say that that's not a function, right? That definition on that prior slide says that in order for a relation to be a function, each element in the set X must map to one and only one element in the set Y. And in this example down here is a function. So this relation is a function because each element x maps to one and only one element in the range. Now here's another example, right? And in this example, this is a function, okay? And the reason why it is a function is each element x maps to one and only one element in the range. Each element in the domain maps to only one element in the range. Here's an element that maps to only 1 in the range. Here's an element that maps to only 1 in the range. Right now in the book, they tried to make this one be a little bit tricky by having this element in the domain map to the same element in the range. This is shared. But that doesn't invalidate the definition of a function. Remember, the definition of a function just says that each element x must map to one and only one element y. And that's happening here. Okay? Now, here's an example again, excuse me, where the relation is not a function, right? And we can see this element in the domain is mapping to 2 different elements in the range. And therefore, it is not a function. Every other element in the domain maps to one and only one element in the range. So all of these satisfy the definition, but this one invalidates the definition. And it only takes one element to break the rule of being a function. All right, so let's take a look at a couple more examples. So instead of mappings, let's look at ordered pairs. So here's an ordered pair. Now remember, these are mappings, right? The element of x equals 2 maps to the element of y equals 3. The element of x equals 4 maps to the element of y equals 1. The element of x equals 3 maps to the element of y equals -2. Right? And what we notice in this particular example is notice that x equals 2 is listed twice. So here, x equals 2 is mapping to 3, and x equals 2 is mapping to -1. So because of that, one of these elements in the domain, x equals 2, maps to 2 different elements in the range. So we're going to say that that's not a function. Now here's another set of ordered pairs, and again, this is a mapping. So this x maps to this y, and when we look at this example, there's no repeated x value. -2, 4, 3, and 2 are all listed one time. So each x maps to one and only one element, and therefore it's a function. All right, so this last example, let's see, we have 2 listed, we have 4 listed, we have 3 listed, and 0 listed. And even though 2 maps to 3, 4 maps to 3, and 3 maps to 3, right, each element of x maps to one and only element in the range. We don't have any repetition there, and so this is a function. All right, so now that we kind of have some illustrated that definition with mappings and ordered pairs, let's get a little bit more realistic into the terms of what we're going to do in this course. So let's suppose we have the equation y equals -1/2 x minus 3, right? And the question basically says determine if this represents a function or not. All right, now this is definitely a relation, but is it a function? So what we want to know is for each x, is there one and only one y? So what I'm literally going to do is I'm going to pick an x value. I picked x equals 4. And when I plug x equals 4 and I get -1/2 times 4, which is -2, and then -2 minus 3 is -5. So if I pick an x value and plug into this equation, I'm going to get one and only one y value. And this would be true for any other x that I pick. So I'm going to say for each x there will be a one and only one y value. This relation does represent a function. All right, now let's determine if this equation represents a function or not. So if we have x equals 2y squared plus 1. So I'm going to pick an x value and I'm going to find the y value that goes with it. So I picked x equals 9. And I'm going to find the y that goes with it. So the first thing I did was subtract 1 from both sides. So I get 9 minus 1, which is 8. And then I'm going to divide both sides by 2. So I'm going to get 4 equals y squared. So what numbers can I square to get 4? Well, that's the square root of 4. Right? So 2 squared is 4, and -2 squared is 4. So in fact, I get 2 y values when I picked x equals 9. So for this particular relation, it is not a function. All right, now the second objective in this section is to find the value of a function. So once we know that we have a function, right, how can we find function values? So the book, this is pretty classic, right? The book gives what's called a function machine, and they talk about I drop in a value of x, and my function, right, my equation operates on it and spits out a value of y. And again, remember that I think the nice thing about this visualization is the idea here is that I put in one x, I get out one y. All right, so let's look at an example with some numbers here. So let's suppose we have the function f of x equals negative 3x squared plus 2x. So let me stop for just a second and point out to you that once we start using this function notation, the f of x notation, right? This is replacing the variable y in the equation. So if I don't use y equals negative 3x squared plus 2x anymore, if I use the f of x or f at x notation, then I'm communicating to you this is a function. So there's no need for me to determine whether this equation is a function or not, because this notation f of x is communicating to you this equation is a function. Now, if you wanted to, absolutely, you could pick an x value and see that you get one and only one y value in return. But again, the advantage to this notation is it communicates to the reader this equation is a function, no need to test it. So let's look at the function notation for a moment, right? So let's suppose letter A, right, says I want to find f of 3 or f at 3. All right, so again, with this notation, what this is saying is we're going to replace x with 3. We're going to plug it into the function machine, and it's going to spit out one y value for me. So I'm going to take x equals 3. I'm going to plug 3 into both x's, and then I'm going to simplify, and I'm going to get one output out of that result. So if I plug 3 in, I'm going to get negative 3 times 3 squared plus 2 times 3. All right, so 3 squared is 9, and then 2 times 3 is 6. So I'm going to have negative 3 times 9, which is negative 27, and then plus 6 is negative 21. So if I plug 3 into my function machine, I get a y value output, right, a function output of negative 21. Now letter B says find f of x plus f of 3. So basically I'm going to take the original function f of x, which was negative 3x squared plus 2x, and then I'm going to plug in 3 and add these together. And I already plugged 3 in letter A, so I know that f at 3 is negative 21. So I have the f at x plus the f at 3. And then I just simplify. There's no like terms for me to really add here. So I got negative 3x squared plus 2x minus 21 as my final result. Now I think what's a little confusing in these, right, when you're new to this function notation, is that f at x, right? This f at x, I didn't plug any number in for x. So this answer is going to have x's in the expression, right? So there's no numerical values coming out here. Notice how I have x's still in my expression, and that's totally okay. All right. All right, oops. Let me back up one. All right, so letter C says find f at negative x. All right, so just like with letter A, I'm going to take negative x and I'm going to plug it into every x variable in my equation. So I'm going to take negative x, I'm going to have negative x squared, and then 2 times negative x. Right? So again, negative x squared, right, is negative x times negative x, which is positive x squared times negative 3. So I get negative 3x squared. And then 2 times negative x is just, minus 2x. So there's my simplified version for letter C. All right, now letter D says find the opposite of f of x. All right, so I want you to notice here, right, this is replacing the inside, right, x with negative x. This is taking the opposite of the equation, opposite of the whole equation. So I'm going to take the opposite of the whole f of x. So when I take the opposite of the entire f of x, right, I'm in essence going to distribute the negative here and it becomes positive. And then I'm going to distribute the negative here and it becomes negative. So there's my simplified version for letter D. And then letter E, the last one, says find f of x plus 3. So again, just like I did with letter A where I plugged 3 in for the x value, just like I did with letter C where I plugged negative x in for the x value, here I'm just replacing the x value with x plus 3, and I'm going to simplify it. So I plug x plus 3 in and I got to square that, and then I plug x plus 3 in here. Right? So again, here's my original equation. I'm going to plug x plus 3 in and square it, and then I'm going to plug x plus 3 in here, and that's the result that I'm going to get here. So if I FOIL this expression, x plus 3 times x plus 3, I'm going to get x squared plus 3x plus 3x plus 9. So remember, FOIL is that I multiply the first together, and that's where the x squared comes from. I do the outside, and that's where the 3x comes from. I do the inside, and that's where the other 3x comes from. And then I do the last. 3 times 3 is 9. And then I distribute my 3 here, right? So here's my final expression when I combine all like terms. All right, so I want to show you something kind of cool here. So let me pull up my calculator real quick. And let's suppose I wanted to do maybe some of this work on my calculator. Now, there's some of this work I can do, and there's some of this work that I can't do, right? So let me go to the y equals screen, and I hit the clear button to clear out the equation that I had there. And what I'm going to do is type in this equation that I have, negative 3x squared plus 2x. So I'm going to come down here to the negative key, and I'm going to do negative, and then do 3. And then I hit my variable button up here. Here's my variable button. And then I'm going to hit the square key right here. So there's negative 3x squared. And then I have plus 2 and then x. All right. So what's cool, one thing my calculator can do for me is it can evaluate some function notation. Now the function notation that my calculator can do is when I have a number in it, right? So when I'm plugging in like letter A, I'm plugging in x equals 3, my calculator can evaluate that for me. So what I can do is once I've plugged into the equation y1, now notice how my calculator is not using function notation, right? It's calling this the equation y1. So I'm going to go to my home screen. So I'm going to do second and hit the mode key, which is the quit, and that's going to bring me to my home screen. So from my home screen, here's what I'm going to do. I'm going to hit the vars key, and you see the vars key is over here. So I'm going to hit the vars key, and I'm going to arrow to the right to the yvars menu, and then I'm going to call out the function. So I'm going to hit number 1, and I'm going to call out the equation that I typed into, which for me was y1. So I'm going to punch number 1 again. So from my home screen, I did vars yvars function y1. I'm not going to do this again, right? But that was how I got to that value, right? So here's my equation y1, and I'm going to literally use parentheses, plug in the number. So using these two parentheses buttons, I'm communicating to the calculator to plug 3 into the equation and tell me the y value. So it'll plug it in for me. Really, really cool that it'll do that. Now, unfortunately, my calculator can't do symbolic manipulation. For example, I can't plug in like letter E. I can't plug in x plus 3 to the equation. It's not going to work. Right? The calculator doesn't do symbolic manipulation for me. Right? Now, that being said, you could go to wolframalpha.com, and Wolfram Alpha, as long as you're doing from the web, is free. You can pay for their app. I think it's like $2, $3. I wouldn't recommend that you do that. I would just use, your smartphone or your computer and go to the website Wolfram Alpha if you want to play with this. And this is not a requirement. It's just something really cool I want to show you. But what you could do is you could evaluate. So let's say we could type evaluate f of x equals negative 2x squared. I think I did that wrong, right? Isn't it negative 3x squared plus 2x at x plus 3? Let's see what happens here. I believe it will interpret what I want, and it will plug x plus 3 in, and then it'll evaluate that for me. And nope, that didn't work. All right, so I think what I have to do is just plug the x plus 3 in. All right, so I think what I can do is this. I can say negative 3 times, and let me put parentheses, say x plus 3 quantity squared, and then 2 times x plus 3. I think I actually have to plug it in first, and then it can simplify this. So let's see if that works. I'm pretty sure this will work. Oh yeah, all right, so we can see that it's typing in for me, but did it simplify the result for me? Look at that. It did simplify the result for me. So negative 3x squared minus 16x minus 21. Is that the same answer that we got? All All right, so look, check it out. That is not the same answer. And so that catches a mistake that I made on the PowerPoint slide here. That was perfect. So look at the mistake that I made here. I started off typing the -3 in on the first line, and then I totally dropped the negative symbol. So when I distributed my 3 into here, I totally left out the negative symbol. So if we bring Wolfram Alpha back up here real quick, we see that what we should have gotten was -3x squared minus 16x minus 21. So let's fix our mistake. All right, so let's come back to this line right here, right? So what I should have, let's come back to this line right here. I should have -3 times, I would have x squared, and then that would be plus 6x plus 9. And then I have the plus 2x plus 6 left there, right? And then I would have -3x squared. And then I would have, this would be minus 18x. And then 9 times 3 is 27, so I'd have -27. And then I have the plus 2x plus 6 there, right? And then, so I got the -3x squared. And then I have the -18 plus 2 is the -16x that Wolfram Alpha showed me. And then I have -27 plus 6, which is the -21 that Wolfram Alpha showed me as well. All right, so Wolfram Alpha caught my mistake for me. All right, and one thing I want to caution you on here when using technology like Wolfram Alpha or the TI, right, is this technology should not replace the by hand work that you're doing, but it is a wonderful, wonderful way to check your work. So make sure that you are practicing this work by hand, right? Just want to mention, right, when you get to UCF is not going to let you use graphing calculators. UCF is not going to let you use Wolfram Alpha. So as wonderful as this technology is, you don't want to only learn the technology. Then it becomes a crutch, and then when you get to UCF, you're not going to do well without the technology, right? It becomes kind of a culture shock to transfer to that institution or any other institution. Most four-year schools won't let you use Wolfram Alpha or TI graphing calculators. Okay, one more thing I want to show you here is Desmos.com. This is really cool. So this is a free web-based graphing calculator, and Desmos.com is the web address. They also have a free app that you can download. You can see right here on their website for either Android or Apple. Also, the website is HTML5 based, so it's device agnostic, right? It can run on any tablet, any computer. You can even go to the website on your phone. It's just because the phone screens are so much smaller than any general tablet. They highly recommend you download the free app. It's a little bit more user-friendly on phones. Anyway, so if we just come to here real quick, I just want to show you the whole idea of that function that we were talking about. So we had y equals -3x squared plus 2x. So again, if I look down here at this key palette, I typed all of that on my keyboard, but here's my x variable, here's my y variable. If I want more letters, I can click the ABC button. I can get parentheses and brackets if I want. But this is the general key that you'll use. Here's absolute value, here's parentheses again, here's how I would square something, here's how I would do a general exponent, and here's numbers, so on and so forth. Okay, I'll show you that you can create an account. It's absolutely free. I would highly recommend that. There's tutorials in there on how to use Desmos. Now, I will show you real quick, right? Here's our function that we were evaluating, and we were evaluating y at 3. So one thing you can do, you can just kind of click on the graph and hold your left button and drag it down until we get to like x equals 3. Where's it at? There we go. And we can see the y value, right? The function value would be -21. One other thing we can do in Desmos is instead of using the y variable, we could use function notation f of x, right? And then if I hit enter and create a new line, I can literally just type f at 3, and it'll tell me what that value is there. So pretty cool that I could do that on my, Desmos. I can evaluate function notation on my calculator, as I showed you, right? Or we can even use Wolfram Alpha to do this symbolic manipulation, right? So Desmos can't do the symbolic manipulation like in letter E, neither can my TI, but Wolfram can do that for me. All right, so this first section is a little bit long because it's introductory and they want to go over quite a few concepts. So we've got 2 more objectives to look at, and I apologize, this video is getting a little long. I've probably got about 8 to 10 more minutes here. So number 3 is finding the domain of a function. Now we kind of already talked about that concept, but what we're going to talk about in this objective specifically is related to equations, okay? So determining whether each relation represents a function, right? And then if it is a function, state the domain and range. So, you know, we did this example already, but just kind of as a refresher, right? So here was an example we looked at earlier where we noticed that x equals 2 mapped to 3 and x equals 2 mapped to -1. So here's a relation that is not a function because there's an x that corresponds to more than one y value. So we're not going to say that there's a domain and range here because it's not a function. But in that second example that we looked at, this was a function, right? So each x mapped to 1 and only one y, and then we're going to take each x value. Those are elements in the domain. So here we are listing the domain in set notation, and then all of the y values are elements in the range. So we're going to say here all the y's that are in the range. And again, in this example we did about 10 minutes ago, the third example was not a function. You know, that's a repeat. So I apologize for that. So, all right, let's move on to what we're going to really see in the homework here, is where we're going to see equations. Right? So again, the domain is a set of all the inputs, right, which we typically represent with the x variable. And the range is the set of the outputs, which we typically represent with the y variable. So if we have an unspecified domain, then typically what we're going to do is we're going to take the largest set of real numbers for which the equation defines a real number output. Right? So again, I only want to plug numbers into the equation where I get real numbers as outputs. So in this first example, we have a square root. Right? And you may recall that the square root of a negative number is not real. Now, typically what we talk about like in an intermediate algebra course is that the square root of a negative is an imaginary number. Sometimes called a complex number. Right? We don't want to deal with those values in this algebra course. So when I plug a number into a function, right, for the x variable, I don't want to have an imaginary output. I only want real valued outputs. So for example, if I pick like, let's say x equals -20, I'm going to get -20 plus 10, which is in the square root of -10. So when I plug x equals -20 in, I'm getting the square root of a negative. So I'm going to say x equals -20 is not in the domain of this function. So how would I find the domain of this function then, right? So really the quickest, most efficient way is to say to ourselves, well, we know this number under the radical, right? This number x plus 10 that's under the radical can't be negative. So what I'm going to do is, since I know the square root of a negative is not real, I'm going to take this number x plus 10 and I'm going to make it be greater than or equal to 0. So I'm going to say the only x's in the domain have to be positive values under the root, right? So x plus 10 has to be 0 or positive. So simply I'm just going to solve this inequality, right? So I'm going to subtract 10 from both sides, and then I'm going to have x is greater or equal to -10, and that is my domain. So again, I picked x equals -20, and that wasn't in the domain, right? And that's because -20 is less than -10. It's not greater than, right? So that's not in the domain. But any x that's greater or equal to -10 would be in the domain. So I could write it in what we call set builder notation, or I could write it in what we call interval notation. All right, so that's the concept of domain. If the domain's not specified by like a set of ordered pairs, then I'm going to have to look at the equation and look at what's implied by the equation. Okay? Just a note for you here. If it's been a while since you've seen set builder notation or been a while since you've seen interval notation in Blackboard under our 3.1 section, there's a couple additional resources that will help you with that, practice that information, right? Or you could go back, I believe it's chapter 2 in our textbook, which has interval notation review as well. And then, of course, don't forget that in the e-text in my math lab, you can always go to the very end, the index, look up the term interval notation, and it'll tell you the exact page that it's on, all right? Use any of those resources to review these notations here. All right, let's look at a couple other examples. So here's a new page with a couple examples. It says find the domain of each of the following functions. So here's a function. Right, and again, I know that this is a function because I'm using function notation, right? So we know this is a function. Let's find its domain. Now, in this particular case, notice there's no square roots in this equation. So I don't have to deal with square roots of a negative, but I do have a denominator. And remember that division by 0 is not defined. So I can't have division by 0. So any x that does not produce division by 0 will be in my domain. Any x that does produce division by 0 will not be in my domain. So what I'm going to typically do, I think the easier path here is say, since we can't have division by 0, I'm going to ask, well, where would I have division by 0? Right, so in this case, if I take this denominator, set it equal to 0, I can factor this expression as x minus 3 times x plus 1. So I get x minus 3 equal to 0, which gives me x equals 3, and then I take x plus 1 equal to 0, and that gives me x equals negative 1. So I have these two x values cannot be put into the denominator, otherwise they would create division by 0. But any other x value is totally legitimate. So the way I'm going to write this, I'll use set builder notation. I think that's the easier way in this case. I'm going to say it's the set of all real numbers x such that x cannot equal negative 1 or 3. And we could do interval notation in this manner as well, but notice it's a little uglier. It doesn't look as pretty as the set builder. So then another example, suppose we have g of x equals x squared minus 9. Now again, in this case, notice there's no square roots. So I don't have to worry about square roots and negatives. And notice there's no denominator. Well, I mean, technically there's a denominator. All of this sits over the number 1. But, there's no x's in a denominator. So I don't have to worry about division by 0 either. So there's no inherent restrictions in this equation. No square roots and negatives, no division by zeros. So there's going to be all reals as our domain. All right, and then third example, square root of 3 minus 2x. Right? So this is just like that very first example we looked at on the prior slide. I can't have the square root of a negative number, so I'm going to take the thing under the radical, the 3 minus 2x, and I'm going to set it greater than or equal to 0. So what I did was I subtracted 3 from both sides and brought it over here, and that gave me negative 2x is greater than or equal to negative 3. And then don't forget, when I divide both sides by negative 2, the inequality symbol has to change direction. So if I divide by negative 2 here, I get x. Divide by negative 2 here, I get positive 3 halves. And the greater than changes to a less than. So I can write this domain as set builder notation and interval notation. Now something I want to show you, on my calculator. So let's suppose this last example here. I bring up my calculator and I hit the y equals button. Let me turn it on. Right? And let me type in this equation. Let me do second square to bring up the square root. I'm going to do 3 and then minus 2 and then my variable x. And then let me close the root here. So here's what's kind of cool about the calculator, right? If I graph, let me do a zoom, and I'm going to punch number 6. I'm going to do a standard zoom window. You can see what's going to happen is the calculator is only going to graph over the domain, right? So notice that any x that is 1.5 or less, that's where the graph lives, right? So it only plots outputs, function values, right? It's only giving me y values where the x is less than 1.5. So if x is less than 1.5, it's plotting values. If x is greater than 1.5, the graph ceases to exist, right? That's where I would get square roots of negatives. So kind of cool with the technology, I can kind of check my work with domain and see where the graph would live, right? Where it would exist. Okay, so last objective for this section. This is a pretty jam-packed section with quite a bit of information, right? We talked about the introduction to the idea of what a function is, right? So we looked at relations and determined whether they were functions or not. We talked about function notation, that f of x symbol, evaluating functions with that function notation. We talked about domain, finding domain of functions, and then the last thing we talk about is forming the sum, difference, product, and quotient of two functions. So what we'll see in this quick example here is that basically if I'm adding two functions, I'm literally just going to add the two functions together, right? If I subtract two functions, I'm going to literally subtract them. I can multiply two functions and I can divide two functions. The only thing we have to remember is that when we divide, we can't have division by 0 here. Okay. So in this example, let's say I have the function f of x equals 2x squared plus 3, and then I have the function g of x equals 4x cubed plus 1. So let's say the first thing we want to find is f plus g. So if I want to find f plus g, I'm literally just going to add f and g together. So I'm going to take 2x squared plus 3, and I'm going to add 4x cubed plus 1. So I'm going to get the 4x cubed, I get the 2x squared, and then the 3 plus 1 gives me the 4. So I'm just going to combine the like terms, and there's my function, f plus g. And then if I subtract, right, I'm going to subtract the two functions. So I'm going to take f minus g. And the only thing to be a little careful of here is when I'm subtracting g, I distribute the negative sign, right, and I subtract every term in the g function. So I got 2x squared plus 3 minus 4x cubed plus 1. And so when I distribute, I get negative 4x cubed. I have the plus 2x squared. And then I get 3 minus 1, which is 2. All right, and then let's multiply. So if I do f times g, right, here's my f function times my g function. I'm going to FOIL. So the first gives me 2 times 2, which is 8, x to the 5th. And then I'll do the outside, right, 2x squared times 1 is 2x squared. I'll do the inside. 3 times 4 is 12x cubed. There's the inside. And then 3 times 1 is 3. And there's f times g. And then the last thing would be the division. So in this case, I'm just going to write f divided by g as f, which is 2x squared plus 3, over g, which is 4x cubed plus 1. And I just want to remember I can't have division by 0. Right? So if I take 4x cubed plus 1, set it equal to 0, I solve for x. Here's the value that x cannot equal, and that is not in the domain. All right, so I want to remind you that there's a really nice summary in the end of each section, and then at the end of each chapter, there is a nice summary of the whole chapter in your e-text. So when you look in my math lab and you're looking at the e-text, you start to prepare and get ready for the chapter test. The chapter review has a really nice summary, kind of all the concepts that you've learned in this section. So again, as a reminder, as you work through all of this material throughout the whole semester, if you have questions on anything, please post on the course discussion board in Blackboard. Ask your peers, ask me. That is our classroom environment for us to ask questions for each other. And I will see you in the